Hello everyone, welcome to session. So today our session is the how to convert the encoder pulse in the RPM. So in the last video I had give the information about the encoder input, how to configure the encoder in the inputs, and which setting is required for the encoder configuration in the TIA portal. That everything I had completed in my last video. So today I will show you how to convert the pulse data into the RPM format. Okay, so RPM is our binary output. So there are the different type of the output we can achieve by the encoder. If we want RPM or line per speed or measurement like in so that everything we can do using this encoder pulse value. Okay, so but it is difficult to cover everything in this video. So today I will be cover only the RPM, how we can convert the encoder pulse into the RPM. Okay, so in this picture you can see here the encoder wiring. One number is encoder wiring and two number is HSC configuration in the TIA portal and the RPM calculation. Okay, so this is the encoder wiring. So how we can do the wiring of encoder means 24-volt supply require, and A and B phase and Z phase. So two phase all enough for these pulses. Okay, so we need to select the input address, means it is connect with the I0.0, I0.1. If you have any other 0 pulse output, so that we can also connect in I0.2. Okay, but A and B is enough, and some setting is we needed. Okay, in HSC configuration means HSC enable configuration counting direction up and counting mode. So that selection we need to do in the 3IA portal. And about the RPM calculation, so this is the equation. RPM is equal to pulse difference into 16,000 and sample times in millisecond into count per revolution. But here the 16,000 is the into 4. The value is quadrature, so into 4, so that it will use 16,000. Okay, so here the use the ladder logic. Okay, and it is need to create in OB30. This is a cyclic interrupt. Okay, and this is the method of HSC current value and previous value comparison, and we can find the pulse difference, and this pulse difference, using this pulse difference we can calculate the RPM. But today I will not show you this type of method. I will show you another different method. It is more easy, and it is widely used in the industries. So that method I will show you in this session. Okay, so about the RPM, so here the RPM is 1024 ppr, but I will show you for the 1000 RPM, so our calculation will be easy. Okay, so in this session I will be cover everything up step by step. I will again repeat the how we can configure the encoder in the TIA portal. That part also I will be cover in this session, and up to how we can convert the pulses into the RPM. So first what we need to do, so first I will create 1 dB. Okay, so here I already I already selected S7-1200 PLC 1214 series CPU. Okay, and now I will be create one OB first. Sorry, I will show you how configuration again. Okay, so it is already available in the main CPU. So open the main CPU properties. In the main CPU properties, so I am selecting here one HSC1, means high speed counter 1. I already selected means address inputs. My input is I0.0, 0.1 and 0.2. So I am using this HSC1. This is my HSC1. Okay, so HSC1 already enable this high speed counter. By default it will be disabled, so we need to enable this one. Okay, enable this high speed counter. Okay, then function, so this is the type of counting is count, and operation phase is AB, and initial counting direction will be count up. Okay, so in count up direction it will be count. and then initial, and then IO address. So this is the our IO address. Okay, so our IO address is 1000 and 1000 ID 1000 ID 1000 our IO address. So I will use ID 1000 address for the pulse. Okay, so I am using the HSC one. Okay, already we are assuming the wiring on input 1. Okay, okay, so I hope it is clear up to here. So how to configure the HSC 1. Okay, okay, now we need to create one DB. Okay, so this DB we will use. Okay, so in this DB I will give the name of DB. I will give the DB name DB underscore encoder underscore data. Okay, then okay. Now in this DB I will add some tags. Okay, just I am removing some tick mark from the properties optimization block, otherwise it is giving the error. Okay, so then okay. Okay, now in this block db1 I will create the 3 tags. Okay, 3 to 4 tags. So first tag live value, means whatever the value come from the ID 1000, that value I will be stored in this tag live pulses. Okay, and then data type will be double integer. Okay, the data type will be double integer. Okay, this is for the live pulse. I will take the another one tag actual RPM. So whatever the calculation finish, and that RPM actual RPM I will store here, and it is in the real format. Okay, and last one is most important. It is the HSC control bit. Okay, so HSC bit control HSC underscore BIT underscore CTRL control, and the data type not real data type HSC underscore count. Okay, so thereafter you can see here so many datas open. Okay, so you can use as per requirement. Okay, 1 to 2 data we will use for our programming. Okay, so you can also use the actual count and another things from the here, and you want to know about the what is the purpose of this all the data, so you can refer the manual. Okay, okay, so these are all the data. Okay, now we need to call the HSC counter. Okay, first we need to compile this block, otherwise again it will give the error. Okay, so why this not going to compile? Okay, going to main OB, and again I will come back to DB1. Okay, okay, now compile. Okay, there is no error in the DB. Okay, so no problem. Now going to back in main OB. Okay, in main OB I will take one instruction. Okay, so instruction available in the instruction right side. Okay, so in the right side, open this one, and the last one is technology. Okay, in the technology, one is accounting. Okay, in counting, one instruction is available, control HSC EXT. Okay, so I am dragging dropping here this one. Okay, and then okay. Okay, now HSC. So if you have any instance ID, so you can directly write the instance ID. Otherwise, you can write the local and select the HSC one. Okay, because we are using right now HSC one, and this is from the local module. Okay, so HSC is coming from the local module. So local HSC one. Okay, so you can check the hardware ID. Okay, 257 is the hardware ID. Otherwise, you can directly write the hardware ID, not an issue. Okay, now control. So for the control, we already make one tags in the DB encoder data in DB1. Okay, so that tag we will use here in a control. So last one is HSC beat control. We will use here. Okay, so our inputs will be DB encoder data into control, DB encoder data and HSC beat control. That's okay. So again the dot is there. So we need to remove the dot. Otherwise, what will be happen? It will show in the RAID format. Okay, because we need not need no need to define another text. We no need to extension. Okay, so okay, right now is okay. Okay, just save and compile. Okay, so this is okay, no an issue, and just compile this one. Okay, so OB1 work is completed. Okay, after OB1 we need to create one more OB, and it's called the OB30. Okay, so OB30 especially for the interrupt block. Okay, so OB will execute as per the time cycle. Okay, so we can set the time cycle. So I am creating one more OB, add new. Okay, add new, and this organization block, and here I am selecting cyclic interrupt. And cycle time, our cycle time is 100 millisecond. Okay, so this block I am using here. This is OB30. Okay, this is specially for the encoder. Okay, then okay. Okay, so OB31 will be open, and we will do the programming in this OB31. Okay, in OB31, first I will move the value, live value. Okay, so live value will come from ID 1000. This is our address. Okay, so I am typing here ID 1000. Okay, and this ID 1000 value, encoder value, I will be transfer. Already I created one DB encoder data in the live value, so I will be used there. Okay, and this is the live pulse. Okay, so live pulse I receive, and I have data. Okay, so that data I will be use. Okay, it's taking time, sometime. Okay, now you can see here the equation. You can see the equation. Okay, RPM is equal to pulse difference into 16. In our case, it will be 16. It will be 16 into sample times into count per revolution. So our count per revolution is 1000. Sample time is 1000 millisecond, and pulse difference means our live pulse will be add here. Okay, and into 16. Here into for quadrature, so it use the 60. Okay, so this is the formula. This formula we will use for the RPM calculation. Okay, but you can see here the HSC current value and previous value will be calculated and generated the pulse difference. So this is the one method to pulse difference, generate the pulse difference, and this pulse difference we can use for the RPM calculation, means RPM generation. Okay, but we are not using this method. We will not use the pulse difference between the current value and the previous value. Okay, we will use directly another method. We will zero the current value every cycle. Okay, this is the method name. Okay, so I hope you understand the RPM formula. RPM is equal to pulse difference into 16 divided by sample time in millisecond into counts per revolution, means PPR, encoder PPR. Okay. Hmm. One minute. Okay. Okay, here use 1024 ppr, but we will use the 1000 ppr. Okay, and sample time is 100 millisecond. Okay, and count per revolution and pulse difference. We already here we can see the pulse difference, current value and previous value. Okay, so now dB encoder data pulse value. Okay, so you can see the our actual RPM in real. Okay, actual RPM in real format. So we need to convert this dB encoder data live into real format, because whatever the data coming from the ID 1000 and transfer this live pulses, it is in the double integer. So our actual RPM in real format, so we need to convert in the real format, otherwise we will convert directly. So I'm inserting here SCL. SCL is good for the calculation. So always use the SCL instead of the ladder instruction. Okay, so how we can use this one? So I'm deleting extra network, so I'm adding here SCL. So first is our actual RPM. So we will receive the final value in our actual RPM. So already we define the tag actual RPM, dB encoder data in RPM. So we will receive the final value in our actual RPM. So already we define the tag actual RPM, dB encoder data into dot our actual RPM. Okay, is equal to, okay, comma is equal to our, as per the our equation is the live pulses. So live pulses already we transfer from ID 1000 to DB encoder data live pulses. Okay, so DB encoder data dot live pulses we will use here. Okay, so just I add one brackets, so it will be more easy to use the brackets. Okay, okay, I already show you formula. So sample time and millisecond and count per revolution. So sample time is 100 milliseconds, so I will be converting the second, so it will be maybe 0.1 millisecond. Okay, so in bracket dB this value dB encoder data live pulses. Okay, into 60 multiplication by 16. Okay, and bracket divided by our sampling time. Our sampling time is 100 millisecond and our encoder PPR is 1000. Okay, so directly I can I can add here directly 100. So we can add like this 0.1, 1000. This is 1000 is our PPR. Okay, but instead of this we can directly use the 100. Okay, 100. Okay, now need to compile one more time, any error is coming or not for checking. Okay, so just need to compile one more time. Okay, so ID 1000 value will come in TB encoder data live pulse. Okay, and this calculation into 60 divided by 100 and we can get the actual RPM. Okay, so actual, but what will be in this case whenever the DB encoder live value will be increased during the rotation of the encoder, so value will be increased, so our actual RPM also will be increased continuously. Okay, it will be also increase the continuously, but this is the not true. We need to require actual RPM. Okay, so what we need to do, we need to reset our actual value, means live value. Okay, we need to reset our live value. So for that I am adding one more network here, because every 100 millisecond I need to reset my live pulses from whatever the value to 0. Okay, so here I am adding one more move button. Okay, and I will use data from the DB encoder data. Okay, control bit, in control bit I will use this bit. Okay, so in this bit new current value I will transfer. Okay, so whenever the complete this cycle, scan cycle complete, end of the scan cycle, I will transfer the 0 value in new current value. Okay, so I am adding here one value is 0. Okay, then I am adding here one register. Okay, we already defined this register in DB encoder data, and the register name is in HSC bit control. In HSC bit control, and the register is new current count. Okay, new current count. Okay, not this, new reference, new current. Okay, new current count. Okay, so end of the scan cycle, my new current count will be 0. Okay, so 0 value will be a transfer in this here, but we need to initialize this 0 means update. We need to update this value by need to on one more bit. Okay, so here for the 0 setting, need to add one more bit, db encoder data in bit control dot encoder cv. Okay, set value, encoder set value, new set value. Okay, so whenever I will transfer the 0 value, so the actual value will become a 0. Then again it will start from the 0 to whatever the encoder rotation, it will give the pulse. Again in the end of the cycle value become a 0, then again 100 0 100 0. Okay, so in this case we not need to add the pulse difference, current pulse and past pulse and current pulse. Okay, so what will be happen, this id 1000 value, this id 1000 value, it will become a 0. Okay, okay, so again start from the 0, so the value will come here, whatever the live value means 100, so 100 into 100 into 16 divided by 100, so it will be our actual RPM. Because the pulse, we are counting the pulse in 100 millisecond time pulse interval. Okay, so whatever the pulse is coming, it will be convert from the RPM. Okay, one more thing, I convert into double integer to real, because our actual RPM in the real format. So I'm adding one more thing, one more instruction, double integer to real, so it will be convert from the double integer to real. Okay, so finally we will receive the data in our db encoder data actual RPM. So we can found the RPM in this register. Okay, db encoder data dot actual RPM. Okay, so this is the process for the RPM calculation. Okay, so using this method, this is the very easy method and mostly used in the industrial this method, so we can use this method. Okay, so but you need to use cyclic interrupt. Okay, 100 milliseconds, so whatever the value will come, that value will transfer here. Okay, and again it will be calculated, and id 1000 value, every cycle it value will be reset, it will be start from the 0. Okay, so db encoder live data into 16 divided by 100, so whatever the value will come, db encoder data actual RPM will show. Okay, and in the next cycle what will be happen, 0 value will move in new current value, and new current value will set automatically using the bit on. Okay, so this is from my side. I hope you understand this process, and this is very easy process. And if you require, I delivered the video in the Hindi format, so let me know or comment, so I will also make the video in the Hindi format. Okay, so final value we can receive in db encoder data dot actual RPM. Okay, so network number 3, the value 0 will be transferred in this db register. Okay, db1 db d32. Okay, so that value, new current value will become a 0, but we need to update this value using the turn on this bit. Okay, so db encoder data dot hsc bit control encoder cv will set to 0, and again it will start from the 0 0 2 1 2 3 4 5 6 7 8 9 10. Okay, so it will be take the 100 millisecond pulses format, okay, for the RPM calculation. Okay, so this is the RPM calculation program. I hope you understand, and thank you so much. Thank you so much for your support, and please do not forget to like video. Okay, and please suggest to your colleagues, because I need to reach 1000 subscriber. Okay, and you, if you want to learn more videos or any specific topics, so please comment, so I will make the video accordingly. So thank you so much everyone. We will meet you in a new video. In next session I will be show you the line speed calculation. Okay, mm per minute, how we can calculate mm per minute. Okay, so that I will be cover in the next video. Okay, so this is the more important mm per minute. Okay, so how we can calculate the mm per minute from the encoder pulse. Okay, so please subscribe this channel. I will update the lots of video. Okay, and whatever that I have knowledge I will also share to you. Thank you so much your support. Welcome.